Development Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello students, I welcome you all to the series of lectures on chemistry, and in today's lecture we are going to learn something about electrochemistry. Myself Vijaykumar N.Nazare from Sri Shanpadurga Higher Secondary School, Bicholim, Goa. This topic is unit number 3 from the standard 12 chemistry. The slide which I have shown on the screen, you can look at the various electronic items. The word electronics has come from the electrochemistry itself. First, we have the clock over there which requires a battery. This battery is nothing but the electrochemistry. Then we have a mobile which also has a battery, is something to do with the electrochemistry again. Then we have a camera over there, UPS, that is the inverter, it requires a battery. Then laptop has a battery. Then we have a torch or calculator, or look at the even e-vehicle, that is which runs on the battery, car which runs on the battery. There are a lot of items, or generally termed electronic, has to do with the electrochemistry. I'm going to show you two famous personalities which are concerned or related to this particular topic. One is Voltas and other one is Galvani, E. Galvani. The two famous scientists which have done a lot of research on this particular electrochemistry, and cells which have discovered by them, they are also named after them, voltaic cell or the galvanic cell. So let's learn what is electrochemistry, definition of electrochemistry. So electrochemistry is a branch of chemistry that deals with the chemical changes produced by electricity. Chemical changes that are produced by electricity, this is one, and the production of electricity by the chemical changes. So we have both here. Chemical reactions produces electricity, or electricity is used to produce the or carry out the chemical reactions. Based on these, two different terms are there, electrochemical cell and the electrolytic cell, which we are going to learn in detail further. Another definition could be, it is a science that deals with the relation of electricity to chemical changes and with the interconversion of chemical energy and electrical energy. That means conversion of chemical energy into electrical energy, or make use of electrical energy to carry out the chemical reactions. I'm going to show you a syllabus for this particular academic year. Due to pandemic situation, government has slightly reduced. There is no much change in this particular topic as such, but I'll just flash on the screen. The red color portion which is shown there, that particular regarding primary batteries and secondary batteries, this particular topic is slightly deleted for this academic year only. Rest everything is there. We are going to learn this particular topic in detail as we proceed further in this lecture. What is basic knowledge required to learn or understand this particular topic? In 11th standard, we have learned one chapter known as redox reaction. The name itself comes from the two words reduction and oxidation. And you have learned a definition of these two, reduction and oxidation, and together it is known as redox reaction. So basic is very much important to understand the concept of electrochemistry, and that is redox reaction. So let's try to revise quickly what is this particular concept of oxidation. Oxidation is a loss of electron. Okay, oxidation is a loss of electron. That is known as oxidation. Second one is reduction. Gain of electron is nothing but the reduction. So when something loses the electron, that is oxidation, and the one which gains the electron, that becomes the reduction. And together, the word is called as redox reaction. Then we also should know how to calculate E naught of cell, that is E naught cell is equal to E naught cathode minus E naught anode, this particular equation which help us to calculate the standard EMF of the cell. I'm going to show you one electrochemical cell, or a Daniell cell, or a galvanic cell, and I'm going to explain this concept to you. Look at this particular cell. There are two compartments. One is zinc, which contains zinc sulfate solution and zinc rod. other one, the red color, is the copper rod and the copper sulfate solution. Now, these two half cells are connected by a salt bridge. This is a U-shaped tube which contains agar-agar gel inside and a slightly salt dissolved like potassium chloride or potassium nitrate, which makes the salt bridge. The function of salt bridge is to connect the two half cells and to complete the electrical neutrality. Then in this particular reaction, flow of electrons take place from zinc to the copper. Okay, through the external circuit they come here. Copper sulfate solution which is here, there are copper ions. These copper ions will accept the electrons that are coming from the zinc, and the copper ions from here will undergo reduction by accepting these two electrons, and you will find a new layer of copper depositing on the copper electrode. So this side there is oxidation taking place, other side there is the reduction taking place. So what will happen after some time to this particular zinc rod? You will find that zinc rod will start dissolving. That means it will become less and less. Why it is becoming less and less? Because zinc is going in the solution in the form of Zn 2 plus ions, and electrons are set free. You will have higher concentration of zinc here, zinc sulfate concentration will increase, and after some time you will find that color of copper sulfate is going to fade. It will become lighter and lighter. Why it is going to become lighter and lighter? It is because the copper ions are accepting the electrons which are coming from the zinc, and they are undergoing reduction. So there left hand side we have zinc electrode which is undergoing oxidation. On right hand side the red color electron there which is the copper electrode that undergoes the reduction, oxidation, reduction. And flow of electron is from zinc to copper, and flow of current exactly opposite to the flow of electron, that is from copper to the zinc. I will just show you this particular in the form of animation. This is the galvanic cell, have a look at it. Same thing which I explained is coming in the form of animation. Oxidation, zinc is going in the solution, electrons are coming externally, bulb is getting lit, copper is accepting the electron, undergoing reduction. Okay. We have seen a concept of Daniell cell or galvanic cell. Now I am going to explain to you the same with reference to if we connect external battery to the same galvanic cell, what is going to happen. Now this is the same diagram what we have learned earlier, zinc sulfate, copper sulfate, zinc electrode, copper electrode, salt bridge, and external battery. You can see there, this particular thing what you see is a zigzag thing, that is the adjustable rheostat or resistant we can say, and we can adjust the external voltage, that is the battery shown there, E external less than 1.1 volt. That means Daniell cell gives you voltage of 1.1, and if you connect a battery outside that particular Daniell cell which is voltage is less than 1.1, under this condition what is going to happen to this particular cell, Daniell cell? When the voltage is less than 1.1, this cell will function normally as it was functioning earlier. That means zinc will undergo oxidation, copper will undergo oxidation, reduction. Zinc oxidation, copper reduction. That is when E external battery which is there, if that is less than 1.1 volt, this is going to happen. Then if you adjust the resistance in such a way, when E external is equal to 1.1 volt, this inside battery also produces 1.1 volt, and if you are connected external battery which also produces exactly 1.1 volt, under that condition what is going to happen? You must have seen that I is equal to 0. That means there is no current flowing to this particular cell. We can see the deflection also shown in the center, same pointing towards up. That means when E external is equal to 1.1 volt, there is no flow of current take place and there is no reaction taking place. That means we can summarize like this: no flow of electrons or current and no chemical reaction is going to take place when you connect a battery in such a way that external battery is 1.1, inside battery also 1.1, there is no reaction is taking place. Now I am going to take third condition, when external voltage which is there is more than 1.1, what is going to happen? Look at the circuit, everything looks to be same, but now the reactions are going to get reversed. That means now copper is undergoing to get oxidation. That means this copper will dissolve in the solution forming Cu2 plus ions, plus electrons are set free. These electrons are going to come external this side, okay, and these electrons which are going to come here, zinc ions from the solution will accept those electrons and they will undergo reduction. So zinc is undergoing reduction, copper is undergoing oxidation when E external is more than 1.1 volt. So to summarize, I am going to show you both in one screen here. Two condition. Middle condition we have seen when E external is equal to 1.1, no flow of current, no chemical reaction. But in other way you can see less than 1.1 electron flow from zinc rod to copper. There it is electron flow from copper to zinc and the current exactly opposite to it. Zinc dissolves at the anode and copper deposits at the cathode under this, and other one we have seen zinc is deposited at the zinc electrode here and copper dissolves at the copper electrode. The reactions are getting reversed. Then electrode potential. We learn about this. What is the electrode potential? A potential difference that is going to develop between the electrodes and the electrolyte, which is called as electrode potential. That means we have seen the electrode, cathode and anode. A potential difference is being developed over there, and that is called as electrode potential. When the concentration of all the species involved in a half cell is unity, that means equal to 1, electrode potential is known as standard electrode potential. So the potential difference which is obtained under standard condition, that potential will be called as standard electrode potential. Then EMF, which is called as cell potential or electromotive force, EMF. The potential difference between the two electrodes of a galvanic cell is called a cell potential. It is measured in terms of volts. So the cell potential is the difference between the electrode potential, reduction potentials of the cathode and the anode. So it is called as electromotive force of the cell when no current is drawn through the cell. So it is the EMF of the cell or the cell potential. Very important thing now, we have learned about oxidation, half cell, reduction, half cell, cathodic compartment, anodic compartment. Now we will see how to represent a cell. So when you want to show the cell in a simple way, represent on a paper, how it is represented. A galvanic cell is generally represented by putting a vertical line, that is two parallel lines between the metal and the electrolyte solution, and putting a double vertical line between the two electrolytes connected by a salt bridge. So zinc sulfate, copper sulfate, zinc electrode, copper electrode. We have seen this particular two half cells giving you a Daniell cell. If I want to show this in a representation of galvanic cell, zinc electrode shown slash with zinc Zn2 plus, that means zinc rod dipped in zinc sulfate solution, that's why shown aqueous. This is solid, separated by two parallel lines indicate that two half cells are separated. Then comes the copper solution on the other side and copper electrode, that is S is not shown there, but it is S. So zinc, generally when you represent a cell, left hand side what is shown is the cell that is undergoes oxidation or the anode. On the right hand side, what is there is the cathodic compartment. So anodic compartment, cathodic compartment are shown. And this is how you represent a cell. Let's take a concrete example where there is a copper sulfate and silver. This is the equation. If you want to find out from this how to find the E cell or E naught cell, it is E naught right minus E naught left, that is the cathode minus the anode. If you look at this equation, you should be able to write what is the cathode reaction and what is the anode reaction. You can see here cathodic reaction, silver accepting the two electrons undergoing reduction to form a metallic silver, and anode reaction, that is oxidation, copper is undergoing oxidation by loss of two electrons. So copper undergoes oxidation, silver undergoes reduction. You should be able to write the cathode reaction, write the anode reaction once the cell representation is given to you or from the chemical equation. So if you want to show the cell representation for this particular cell, it is this way. Left hand side anodic, right hand side is the cathodic. So copper undergoes oxidation, forming Cu2 plus ions, 2 electrons are set free, it goes that side. Silver accepts the 2 electrons and undergoes reduction to form metallic silver. So E cell is equal to E right minus E left, that is E cathode minus E anode. You can write like this. Then how to measure the electrode potential or measurement of electrode potential is one important aspect from this electrochemistry topic. Potential of individual half cell cannot be measured. You just cannot measure a potential of half cell. So what you are supposed to do for that purpose? We can measure only the difference between the two half cells or difference between two half cell potential that gives the EMF of the cell or electromotive force of the cell. Then for this purpose, since you cannot find out the single potential of a cell, we have to arbitrarily choose potential difference of one electrode, that is one of the half cell, then that of the other can be determined with respect to this. So arbitrarily you have to fix a particular value for one half cell, then you can combine with that cell and find out the electrode potential of the other. For this purpose, a simple electrode called as standard hydrogen electrode is used. I am going to show you the standard hydrogen electrode. According to convention, a half cell called standard hydrogen electrode represented by platinum/hydrogen. Platinum is a material which provides the space to reaction to take place. Platinum/H2/H plus, that means there is a concentration of maybe HCl which is having H plus in that particular solution, is assigned a zero potential at odd temperature. So in standard hydrogen electrode, electrode potential is arbitrarily fixed as 0 and then it is coupled with the another half cell to find out the electrode potential of the other. And the reduction potential is given like this: H plus aqueous plus electron, except the electron undergoes reduction and gives out the hydrogen gas. Many times this question comes, draw a standard hydrogen electrode diagram. Then you should be able to explain this particular diagram in a simple way. In this case, this is like a glass. If you have remember a test tube, it is like inverted test tube. Inside there is a finely divided platinum coated with platinum foil. This square portion is the platinum coated with platinum foil. There is an arrangement for hydrogen gas to bubble inside from this particular portion, and you can see the bubbles coming out. These are of hydrogen here. So how does this particular hydrogen gas is bubbled at a pressure of 1 bar, and the concentration of HCl or H plus here is 1 molar. I am going to show you one small video here about this standard hydrogen electrode. The SHE stands for standard hydrogen electrode, consists of platinum wire that is connected to a platinum surface in contact with an aqueous solution containing 1 molar H plus, which is in equilibrium with H2 gas at a pressure of 1 atmosphere inside. You can see there hydrogen gas is bubbled around the platinum electrode. Molecular view is shown there. The platinum surface catalyzes the oxidation of hydrogen molecule to protons or the reduction of protons to hydrogen gas. Both the reactions are taking place. At the electrode, hydrogen gas can either be oxidized to form hydrogen ions or hydrogen ions can be reduced to form hydrogen gas. So both possibilities are there. So both the reaction, oxidation as well as reduction are shown there. H2 undergoes oxidation to forming 2H plus 2 electrons are set free, and H plus ions accept the 2 electrons, liberating the hydrogen gas. So E naught of this particular is fixed as 0.00 voltage. Arbitrarily, electrode potential of this SHE is fixed as 0.00. So let's try to couple this SHE with now zinc electrode to find out the cell potential of zinc electrode. So zinc is undergoing here oxidation, which is coming from that side. H plus ions are accepting that and is undergoing reduction over there, and the value shown is 0.76. Because cell potential of this is 0, the value comes out for zinc, it is minus 0.76 you will find. That means zinc preferably undergoes oxidation and not the reduction. So on the potentiometer it is showing 0.76. This is the salt bridge to maintain the electrical neutrality. There you might be seeing there it is showing minus 0.76. When we calculate, it comes out to be minus 0.76 because we have of standard hydrogen electrode as 0 volt. Okay, let's move further. There is something called as inert electrode. There are some electrodes which are inert, they do not take part in reaction, but they provide some surface for the reactions to take place. Some metals like platinum or gold are used as inert electrodes. They don't participate, as again I mentioned you, there are some of the reaction here which requires this inert electrodes to carry out the reactions. Platinum in this reaction, okay, then we have bromine electrode reaction, again a platinum. So platinum provides the space, it could be even silver. Then what is the electrochemical series? With respect to electrochemistry, there is one more important concept. Electrochemistry series is a series where many elements are placed in such a way that their electrode potential are given, their standard reduction potentials are given or arranged in a particular series. This particular series is known as electrochemical series, where hydrogen exactly in the center with cell potential or electrode potential fixed as 0. So this is that particular electrochemical series which we are talking about. You can see here hydrogen value at the center shown to be 0.00 there. Okay, this is 0, and all the elements which are placed below hydrogen, they are shown with the negative value. That means their reduction potential is shown with the minus value. That means they undergo oxidation. And all the elements which are placed above the hydrogen, they are undergoing reduction with high reduction potential values are shown there. I am going to show you same thing in a different pattern here with the 2 arrows. In what way? Increasing strength of reducing agent. So if you find out which particular is the most or strongest reducing agent, this is the increasing strength of reducing agent, arrow pointing downwards, lithium. And other side, we have increasing strength of oxidizing agent, which start from this side and goes towards the up. So increasing strength of reducing agent and increasing strength of oxidizing agent are exactly in a different or opposite manner. One equation is very important from standard 12 point of view, that is called as Nernst equation. Let me explain this, what is Nernst equation. Nernst equation is an equation relating the capacity of an atom or ion to take up one or more electrons reduction potential measured at any condition, so that standard condition, which stand for STP or standard reduction potentials of 298 Kelvin and 1 mole or 1 atmospheric pressure. So Nernst equation for a single electrode potential, when there is only one single electrode, how it is expressed? E cell is equal to E naught minus RT upon NF ln Q. Ln stand for exponential form, Q stand here for species that has undergone oxidation divided by reduction, where E cell is equal to cell potential, E naught is equal to cell potential under standard condition, R is a universal gas constant, T is the temperature, N, very important, number of electrons transferred that take place in the redox reaction or electrochemical reactions. F is a Faraday's constant, value all of you know, it is 96,500 coulomb roughly. Q is a reaction quotient. For a reduction reaction, Nernst equation for a single electrode potential for a can be written like this: Mn plus, that means number of electrons that are lost, plus n times electron gives you n times m. And we have equation like this. which is almost everything same, 96,500, value actually is 96,487. R is the gas constant. In the problem, we will be using this formula, 8.314 joule per Kelvin per mole. Then Nernst equation at 25 degrees centigrade. Most of the times problem it is asked under 25 degrees centigrade. For measurements that are carried out at 298 Kelvin, Nernst equation can be expressed as follows. And in most of the problems, we are going to use this particular equation only. E cell is equal to E naught, that is the standard cell potential, minus 0.0592. When we substitute all those values, R, T, that is F, we get this particular value 0.0592 divided by N. N stands for number of electrons that are accepted or lost in the equation. Log to the base 10 Q. Q stands for species concentration that has undergone oxidation divided by the molar concentration of species that have undergone reduction. Therefore, as per the Nernst equation, the overall potential of an electrochemical cell is dependent on the reaction quotient, that is Q. So please remember this particular equation, E cell equal to E naught cell minus 0.0592 divided by N log Q. Q stands for molar concentration of oxidized species divided by molar concentration of reduced species. This particular equation is very important. I am going to show you Nernst equation with one example here. Nickel slash Ni2 plus separated by salt bridge with Ag plus and Ag. In this equation now we understood that left hand side undergoes oxidation, that is anodic compartment, that side is the cathodic compartment, that is the reduction is taking place. So here nickel undergoes oxidation, losing 2 electron. Silver accepts this 2 electron and undergoes reduction. How to write equation for this? We have a cell reaction which can be written in this way. 2 silver, because this is going to, Ni is going to give you 2 electrons after losing Ni2 plus. So 2 electrons have to be accepted by 2 different silver ions to forming, getting reduced to 2 Ag metallic silver. So Nernst equation for this particular thing can be written like this. So you have to pay attention here that whenever this concentration is 2 times or 3 times or 4 times, then that particular species is raised to that particular number. So in silver it is raised to 2 because here stoichiometric coefficient is 2. That's why here you find it as raised to 2. So this is for E cell equal to E naught cell minus RT 2 because number of electrons transfer involved is 2. And this is the not the logarithm form, it is the exponential form. So ln. So if you replace this by log, then you will get that 2.303 RT by 2F. And if you substitute all the values at 25 degree or 298 Kelvin, this could be written as E cell equal to E naught cell minus 0.0592 divided by 2 log of Ni2 plus, that is molar concentration of Ni2 plus divided by molar concentration of silver ions raised to 2. And for any general reaction which is A times A with the stoichiometric coefficient B times B, giving you or losing the N electrons forming CC and DD, C times C, D times D. Nernst equation can be written as E cell equal to E naught cell minus RT NF ln Q, or E naught cell minus E cell equal to E naught cell minus RT upon NF ln. So just replace that ln by log, you will add additional 2.303 over there. Let's try to understand one more concept with respect to this. Consider a metal in contact with its own salt aqueous solution. Reactions of metal losing an electron to become an ion, gaining electron to return the atomic state are equally feasible and are in the equilibrium state. M n plus n electron giving you n times m. In the reduction reaction, n moles of electron is taken up by ion against the reduction potential of ERED. So first concept, the work done in moment of electron. How the work done is equal to work reduction is equal to N F E reduction, where F is a Faraday's constant, that is 96,487 coulomb, which is equal to electrical charge carried by 1 mole of electron. Then change in Gibbs free energy. So generally when a spontaneous reaction takes place, there is a relation between this Gibbs free energy. So combining work done and Gibbs free energy, we have this equation. Work done is equal to NF E reduction, which is also equal to minus delta G, or delta G equal to minus NF E reduction. Then there is one more concept from chemical equilibrium. Last 11th standard we have learned this, something called as equilibrium constant Kc. We can also find out equilibrium constant Kc from this equation. So equilibrium constant using Nernst equation or relation between them. In the circuit in Daniell cell is closed when we note that the reaction, this particular reaction takes place. Zinc undergoes oxidation, copper undergoes reduction. This reaction takes place. As the time passes, the concentration of zinc ions keeps on increasing. So I told you that as time processes or time progresses, concentration of zinc ion will keep on increasing. What will happen to the concentration of copper? It will keep on decreasing. Why it will keep on decreasing? Because Cu2 plus ions from the copper sulfate solution is undergoing reduction. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. So you will find that after some time, it will not show the same voltage of 1.1 volt, but it will start decreasing. After some time, there is no change in the concentration of copper and zinc ions, and at that same time, voltmeter will give you 0 reading. There is no further change is going to occur between concentrations of copper ions and the zinc ion, and voltmeter will finally show you the 0 reading. So this indicates that the reaction now has attained a equilibrium. That means both the reactions are occurring at the same rate. In this situation, we can write the Nernst equation like this: E cell is equal to 0 because no reaction takes place, so value will be equal to 0, which is equal to E naught cell minus 2.303 RT by 2F, because for that equation it is 2 log molar concentration of zinc ions divided by copper ions. So we can rearrange the equation, same equation I wrote here again. After rearranging, what happens? This 0, we take it this side. If you take E naught cell this side, you are going to get E naught cell is equal to 2.303 RT by 2F log molar concentration of zinc ions divided by copper ions. So at equilibrium, we know that these two concentrations are becoming equals, is equal to Kc for the reaction 3.1, that reaction is this. So at temperature 298 Kelvin, the above equation we can rewrite as E naught cell is equal to 0.059 divided by 2 log Kc. So we have this now expression which between equilibrium constant Kc and the E naught cell. So log Kc will be equal to 1.1 into 2 divided by 0.059. That log Kc value will be equal to 37.28, and if you take an antilog of that, we are going to get this value 2 into 10 raised to 37 at 298. So in general, E naught cell will be equal to 2.303 RT upon NF log Kc. So now we have removed that 2, we are using this equation. This equation will be very important for you from examination point of view to solve the problems based on E naught cell and the equilibrium constant Kc. So it gives the relationship between equilibrium constant of the reaction and standard potential of the cell in which that reaction take place. So thus equilibrium constant of the reaction, which is very difficult to find by any other method, we can find it by using this formula, making use of EMF of the cell or E naught value of the cell. Then there is a relation between electrochemical cell and the Gibbs free energy. When a cell reaction takes place, electrical energy is produced which results in decrease in free energy. So free energy concept we used in last year in thermodynamics, G, which stands for Gibbs free energy. There is decrease in Gibbs free energy take place when electrical reaction take place. So electrical work done is equal to decrease in free energy in an electrochemical cell. So electrical work done is nothing but it equal to quantity of current produced into EMF of the cell. So for 1 mole of electrons, quantity of current is 1 Faraday. So when 1 mole of electron flow take place, the current produced is 1 Faraday. That is 96,500 coulomb. Therefore, for n moles, it is n times F. This is the derivations in a simple way shown to you. Electrical work done, NF E cell, which is related to Gibbs free energy minus delta G, equal to NF E cell, or a standard cell minus delta 0 standard condition equal to minus NF E naught cell. So for equilibrium, we have E naught cell equal to RT upon NF ln Kc, and if we replace this ln with exponential form, it becomes logarithm Kc. Value will come there as 2.303. So minus delta G naught is equal to NF into RT by NF ln Kc, which is equal to RT ln Kc, or delta G is equal to minus 2.303, because I am replacing this ln with log now, 2.303 RT log Kc. For a reversible equilibrium reaction, delta G, which is equal to delta G naught plus RT ln K, where K is equilibrium constant, it is a product by reactant, R is the gas constant, T is the temperature in Kelvin scale. This particular triangle-like structure, which is giving you three different concepts, how they are interrelated. The relationship between the Nernst equation, the equilibrium constant, and Gibbs energy. K stand for equilibrium constant, E cell for E naught cell, delta G for standard Gibbs free energy. All equations are important. First, delta G naught equal to minus RT ln K, second one E naught cell equal to RT by NF ln K, and third one delta G naught equal to minus NF E naught cell. So remember these three equations, bear interrelation, because any of these values could be given and values of other could be asked in problem solving. Let's continue further with know that there are some solutions which will conduct the electricity. So generally conductance in electrolytic solutions we are going to learn now. The conductivity of electrolytic, which are produces ionic solution, depends on some factors. We are going to see which are these factors. The nature of the electrolyte added, whether it is a strong electrolyte or a weak electrolyte, that decides about the conductivity of that particular solution. Then comes size of the ion produced and their solvation, that is solute-solvent interaction that they form, that is called as solvation. Based on what is that solvent, that decide. If it is a water, it is called as hydration. Then third factor, nature of solvent, whether that solvent is polar or non-polar, and also its viscosity will decide about the conductivity of the solution. Then comes the concentration of electrolyte. That will be another factor which will going to decide about conductance of the electrolyte solution. And next one is temperature of the solution, which conductance you are measuring. We know these terms resistance and resistivity. In physics we have learned this. The electrical resistance of any object is directly proportional to the length. Okay, suppose this is the length, and inversely proportional to the cross section of the area, LA. These two important terms to find out the resistance of a particular wire or a plate. Resistance is nothing but the obstruction that is being given for the flow of electrons. So that is the resistance. So R is directly proportional to L by A, and R, if we remove the sign of proportionality, we get one constant, which is equal to R is equal to rho equal to L upon A, where rho is the resistivity, or it is also known as specific resistance. So when you remove the sign of proportionality, we get that constant. That constant is nothing but the specific resistance or resistivity. So SI units of this particular resistance are ohm meter. So resistivity can be defined as resistance offered by the conductor of 1 centimeter length and cross section area of 1 centimeter square, that is the resistivity. So what is shown there as rho, that is the resistivity, and it is obtained when we remove the sign of proportionality, R directly proportional to L by A, R equal to, that is nothing but the resistivity. Resistivity and resistance, and now we are going to learn conductivity and conductance. And resistance and conductance, they are inversely proportional to one another. They are exactly opposite. So now comes conductance or conductivity. Conductance is nothing but the ease with the current flow. We have seen that resistance is nothing but the opposition offered for the flow of current. Now here, how easily the electron flow take place, that is the conductance. So it is the inverse of resistance. So K is equal to 1 upon rho L by RA. So you come across G, which is equal to 1 upon R, A upon PL, which is equal to K A by L. So SI unit of conductance is Siemens, equal to ohm inverse, also known as MHO. We can write as MHO, opposite of OHM, ohm, or ohm inverse. The inverse of resistivity is called as conductivity. Okay, inverse of resistivity will be called as conductivity, and here it is known as specific conductance K, that is also called as kappa. The SI unit of conductivity are Siemens meter inverse, or K is expressed in S Siemens centimeter raised to -1. Then equivalent conductivity and molar conductivity. If you know the definitions of what is equivalent weight and molecular weight, you can easily understand what is equivalent conductivity and what will be the molar conductivity. Conductance of a solution containing 1 gram equivalent of a electrolyte which is placed between two electrodes 1 centimeter apart. So it is the equivalent conductance of a solution containing 1 gram equivalent of electrolyte which is placed between two electrodes and their separation distance is 1 centimeter apart. So lambda equivalent stands for equivalent conductivity, which is equal to kV, where V is equal to volume containing 1 gram equivalent. So lambda equivalent is equal to K into 1000 divided by C, 1000 refers to that. Then comes the molar conductivity. As I told you, it is something to do with the molarity or the molecular weight. Lambda m we call it as conductance of solution containing 1 gram mole of electrolyte placed between two electrodes of 1 centimeter apart. Lambda m, which is equal to K into 1000 divided by m. So conductivity of an electrolyte solution divided by the molar concentration of the electrolyte gives us the molar conductivity. So units of molar conductivity, Siemens per meter per molarity, or Siemens meter square mole inverse. Lambda or lambda m both can be used. Molar conductivity denoted by the symbol which I already shown it to you. Lambda m stand for Greek. It is known as lambda. It is related to the conductivity of solution by the equation molar conductivity lambda m, which is equal to K by C. How to measure this conductivity? There are something called as conductivity cells. Measurement of conductivity is done using these cells because you cannot take the solution and directly connect to the electrical wire to find out its conductivity. So what is done is that solution is taken in this particular conductivity cell, then connected to one of the component where you can measure it, and that gives us the conductance of the solution. It consists of two platinum electrodes coated with platinum black finely divided metallic platinum is deposited on the electrodes electrochemically, that is by electroplating method. These have an area of cross section equal to A and are separated by a distance L. Solution confined between the two electrodes. The resistance of such a column of solution is then given by the equation. Now here one important term which you also learned in Wheatstone bridge network or Wheatstone bridge, which is called as physics, you might come across this. It is used to find out the resistance of unknown solution. So if we know the same way resistance of unknown solution, we can also find the conductivity of unknown solution. I will just explain this to you, what is the Wheatstone bridge network and how does it help us to find out the conductivity of a solution. These are R1, R2, R1, R2, R3, R4. 4 different resistors are connected. In between the P stand for a detector. This detector could be either a null deflection or it could be a, it will like a headphone or a earphone where it will give you zero sound in between. Now these are the known values. R1 is a variable resistance, R3, R4 fixed. Why this is variable? Because this you can adjust to get the null deflection whenever, and what is the value you have decided, that value is shown on your rheostat when you adjust that particular value. So you know the value of R also. So how to find unknown resistance is given here. R2 will be equal to R1 into R4 divided by R3. So instead of here 1, 2, 3, these are the resistance. The fourth one here, what is taken, which you want to find R2, that is the conductivity of cell, and that there you are going to find the resistance offered by that particular solution. And if you want to know the conductivity, resistance and conductance, they are inversely proportional to one another, you will get the conductivity of that solution. So this is the conductivity cell. So measuring the resistance of an ionic solution, making use of this Wheatstone bridge. Two types of conductivity cells I am going to show you here. The solution whose conductivity you are going to find out, that is taken in this, and then two terminals are connected in that particular unknown resistance which was mentioned. Either you can have this or this. You have to dip this in a solution. Here directly solution is taken inside, and this you have to dip inside that particular solution whose conductivity you are going to find out. So resistance will be given by R, which is equal to rho, resistivity L by A, which is also equal to L upon K. The quantity L by A is called as cell constant, denoted by the symbol G star, and this value G star is fixed for a particular cell. It is given by a company saying that our cell constant value is so and so. It is given by this equation L by A. So K is equal to cell constant by R, which is equal to G star by R. Next is variation of molar conductance. In what way the conductivity of this solution changes or varies? First one is nature of electrolyte, then comes concentration, and third one is temperature. First one, on the nature of electrolyte. Strong electrolyte which completely ionized in aqueous solution, they have high molar conductivity. Strong electrolytes will have high molar conductivity. Examples are acid like HCl, sulfuric acid, bases like NaOH, KOH, even salts like KCl, NH4Cl, ammonium acetate, they will have high molar conductivity. Then there are weak electrolytes which do not completely ionize in water, they will have low value of molar conductivity. So molar conductivity of weak electrolytes is low, molar conductivity of strong electrolyte is high, and examples here under weak electrolytes, which is a weak acid, acetic acid, weak base, ammonium hydroxide. Then second factor is concentration, which increases with molar conductivity. We have seen increases with dilution. As you dilute the solution, molar conductivity keeps on increasing. This is one of the chart given here. For a 0.1 molar solution, it was 391 for HCl solution. But when you dilute it to 0.001, you find that conductivity is increased up to 421.36. So this is how the molar conductivity depends on concentration. On dilution, molar conductivity increases. Same example with respect to graph, variation of molar conductivity of both are shown there, weak electrolyte and a strong electrolyte. Molar conductivity of electrolytes, one more example, one more graph. Molar conductivity increases with infinite dilution or decrease in concentration. You can see here, high at higher concentration, keeps on decreasing like this. So molar conductivity increases with infinite dilution or decrease in concentration. Decrease the concentration, you will have high molar conductivity. Then, very important law, Faraday's first law and Faraday's second law. Let me tell you what is Faraday's first law. The amount of any substance deposited or liberated at any electrode is directly proportional to the quantity of electricity passed through the electrolytic solution. That means the amount of substances that is liberated or deposited depends on how much amount of electricity is passed through the solution. That is nothing but the Faraday's first law. So it is given by W directly proportional to Q. If I remove the sign of proportionality, I get Z into Q. So this Q is nothing but the I into T, current passed for how much time. Therefore, W is equal to Z into I into T. Sometimes this could be asked in problems to find out the value of W. Then we have Faraday's second law, which says that when same quantity of electricity is passed through different electrolytic solution which are connected in a series, the weight of the substances produced at the electrode are directly proportional to their chemical equivalent weight. That means if you are passing the same amount of electricity, then amount of substance deposited or liberated, that is depending on its chemical equivalent weight, decides how much will be the quantity liberated or deposited. Then there is something called as, very important from this topic is cells. Primary, the cells are of two types, primary cells and the secondary cells. Primary cells are those which we use once and throw them out, or a battery, single cell. After some days it gets discharged, then you have to throw it out. But there are some batteries like your laptop battery, computer battery or inverter battery, it can be recharged again and again. We call those batteries as secondary batteries. So right now the battery topic is not included in this particular year's syllabus. So I'll just restrict myself only for this particular definition of a primary cell. So those particular cells which can be recharged, which cannot be recharged, just you have to throw them after one use. We call them as primary batteries or primary cell, and the batteries which we can reuse them again and again, we call them as secondary batteries. So lead accumulator is an example of secondary batteries. Your chargeable batteries are examples of secondary batteries. One such example here, mercury cell which we use and throw it out. Small cells, cell potential is 1.35 volt here. Another chargeable batteries, secondary batteries, which we can use for a long time, recharge them again and again. This is how it looks like, nickel cadmium cell, but since it is not there in your syllabus for this academic year, we'll just skip this part. Next comes fuel cell. Very important cells. Again, a fuel cell, that means cells which makes use of the fuel energy. So first we'll see definition. Galvanic cells that are designed to convert combustion energy like hydrogen, methane, methanol, etc. directly into electrical energy are called as fuel cells. So I'll repeat again, galvanic cells that are designed to convert energy of combustion or combustional energy of fuels like hydrogen, methane, methanol directly into electrical energy are called as fuel cells. One such fuel cell we are going to learn, that is hydrogen oxygen fuel cell. So you require only two gases, one side hydrogen, other side hydrogen. Put this inside the compartment, you are going to get product as water, but then when this hydrogen oxygen combine, okay, you are going to get energy out of it. That is called as H2O2 fuel cell. So one of the most successful fuel cells used reaction of hydrogen with oxygen to form water. The cell which was used for providing electrical power in the Apollo space program that was used by America, the space program that was launched, and the water that was generated, that water the astronauts they used to drink this particular water, that was a byproduct of this two particular H2N oxygen gas. The water vapors produced during the reaction were condensed and added to the drinking water supply for the astronaut. So in this cell, hydrogen and oxygen are bubbled through porous carbon electrodes and concentrated aqueous sodium hydroxide solution. These are the carbon electrodes. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of the electrode reaction. The electrode reactions are given below. This is the cathode reaction, anode reaction. One side oxygen gas where it is passed, cathode reaction, reduction take place, O2 plus H2O plus 4 electrons, it forms 4 OH minus, and the other side anode, the hydrogen gas which you are bubbling reacts with this 4 OH minus, that is aqueous solution, forms water and 4 electrons are lost. So you have here hydrogen, anode, oxidation, oxygen gas, cathode, reduction is taking place. I am going to show you the diagram of this fuel cell. Very important diagram, though it looks simple, but from exam point of view, you should be able to draw it correctly. People make mistake here. Show the arrow of hydrogen pointing inside. That means H2 fed this side, oxygen from the other side. The electrodes which you see here, these are the porous electrode. That means hydrogen gas can diffuse through it, enter inside. Same way, oxygen gas can diffuse through it, enter inside. We have an aqueous electrolyte inside, maybe NaOH or KOH. This is the anode where hydrogen is there, oxygen, cathode, because these are the reactions that are taking place. So one which undergoes oxidation, that will be anode, one which undergoes reduction, that will be the cathode, and you have to show water coming out from the cell. So that means here water is produced. So H2 and O2, these are the fuels from which we generate the electricity. That's why this is an example of a fuel cell, and fuel cells are of many types, but example which is there for you is H2O2 fuel cell. So once again the equations which I already told you, an overall reaction or the redox reaction, twice H2 plus O2 giving you twice water, that is the product which is obtained in this particular reaction. Importance of fuel cell, why they are very important? The cell runs continuously as long as reactants are applied. That means as long as your H2 and O2 are fed inside your fuel cell, it will start working. Produce electricity with an efficiency about 70% compared to thermal plants whose efficiency is only 40%. So high efficiency. There has been tremendous progress in the development of new electrode materials between better catalysts and electrolytes for increasing the efficiency of fuel cell. One more important point. These have been used in automobiles on an experimental basis. They are tried, and very important with respect to environment. They are pollution free. Then last topic from this topic, this chapter electrochemistry is corrosion. Corrosion is nothing but the rusting, and the entire world loses lot of economy because of this particular simple chemical reaction, corrosion, a very slow chemical reaction which is known as corrosion. And this corrosion is an electrochemical process, and let's see how does this corrosion is electrochemical process. Corrosion slowly coats the surfaces of metallic objects with oxides or other salts of the metal. Generally we find the rust as a oxygen of that particular metal. Rusting of iron, tarnishing of silver, that is silver reacts with this sulfur forming silver sulfide. Development of green coating on copper, that is formation of copper carbonate. You must have observed copper utensil, if you keep for a long time, they turn greenish color. Then same way bronze are some of the examples of corrosion. But main thing is rusting of iron. A lot of things are getting wasted because of this. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxide. So corrosion of iron, commonly known as rusting, occurs in presence of water and air. Both things are necessary. Without these two things, the corrosion or the rusting doesn't take place. Only dry air is there, rusting will not take place. Only water is there, again, rusting or corrosion will not take place. So both are important and essential condition. We know that Goa is very close to the sea, and we have a lot of rusting, or bungalows which are very close by to this particular coastal beach. You find that their grills or things are getting rusting very fast. The only reason is that factor is adding to the factors which are favoring the corrosion. So corrosion is an electrochemical process. So we'll see this particular concept. How does the reaction take place? Imagine this is a piece of iron metal, and there is a water droplet on top of it. Water has come on a iron piece, and you can see here the piece is getting rusted. That means it is going in the Fe2 plus, and 2 electrons are set free. So 2 such electrons giving you 4 electrons, that is reacting here with water. So I can tell you the equations. Anode, iron undergoes oxidation, giving the 4 electrons set. These 4 electrons are accepted by oxygen to form water. Oxidation, reduction. And in atmospheric, this reaction take place. So this is a simple way to represent how does the rusting take place in our daily life. And corrosion is a electrochemical process. So electrons released at anodic spot move to the metal and go to another spot on the metal, reduce oxygen in presence of H+, which is believed to be available from the H2CO3. Formed due to dissolution of carbon dioxide from air and water. Water droplet is there, carbon dioxide is there, it reacts with that, forms carbonic acid. So this spot behaves as a cathode with the reaction. So overall reaction is like this. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which come out as a rust in the form of hydrated ferric oxide. So this is the final product of rusting or a corrosion. You will see a red color spot on top of it, or slightly bumpy portion on a smooth iron rod, and that is nothing but the ferric oxide formation take place, and that is how the rusting take place. If you scratch, you will find that the metal plate will be rusted over there, and with further production of hydrogen ions. So Fe2O3 dot H2O is the formula of rust. How can you prevent corrosion? There are so many methods people are using to prevent the corrosion. Covering the surface with paint, first is the simple way, just apply a coat of paint. Another simple method is to cover the surface by other metals. We call it as galvanization, like tin, zinc. If you use the zinc, it will be galvanization. Or galvanized iron, we call it as Then electrochemical method is to provide a sacrificial anode method of another metal like magnesium, zinc, etc., which corrode itself but saves the object. Sometimes we have iron pipeline which carries the water, and we don't want that particular pipeline to get rusted. So that time what is done, a sacrificial anode method is used. This particular pipeline is connected by using a small zinc rod, and this zinc rod undergoes itself oxidation, doesn't allow the pipeline to get rust. That is known as sacrificial anode method. So thank you very much. That's the end of this particular chapter.
Prudent Scholars, powered by Lupin Pharmaceuticals.